Welcome to What Did the Code Say? I'm your host, Dragon Megalodon. Subscribe to the channel and hit the bell right now. Today in this explainer, we're looking at the underlying code of reality itself, coordinate geometry, and functions. We'll start with simple dots on a plane, and by the end, you'll be transforming complex curves like an absolute pro. We are taking raw algebraic formulas and turning them into pure visual intuition. Let's go.
Here is the roadmap. 1. Points, distances, and midpoints. 2. Equations of circles. 3. Lines, slopes, and intercepts. 4. What is a function? 5. The function toolkit. And finally, 6. Transforming those toolkit functions.
All right, section 1. Points, distances, and midpoints.
Before we build complex graphics, we have to understand the fundamental logic between just two distinct points. Now, the crucial thing here is that the distance formula is not some arbitrary magic trick you need to blindly memorize. It's literally just the Pythagorean theorem in disguise. Draw a right triangle between any 2 points. The horizontal distance is your A, the vertical distance is your B, and the direct line between them, that's the hypotenuse, your C. a² plus b² equals c². Take the square root of both sides, and boom, you've got the distance formula.
Finding the exact middle of a line segment connecting those points is actually beautifully simple. No complex algorithms here. You're literally just taking the average. Add the two x coordinates together, divide by 2 to find the horizontal middle, and do the exact same thing for the y coordinates for the vertical middle. Extremely straightforward.
Moving on to section 2, equations of circles.
Let's take that distance formula and see how it scales up into something way bigger. This brilliantly illustrates how a circle is really just an infinite loop of points mathematically locked at a set distance, the radius, from a specific center point. Look closely at this formula. It is exactly the distance formula we just decoded, but squared on both sides to get rid of the root. The x minus h and y minus k just represent the distance from any point on the outside back to the center at h, k.
But what happens when a circle's equation is hiding in a messy syntax? To refactor a long algebraic string, we use these 4 steps to complete the square. You divide out the leading coefficients, group your x and y terms, have the middle coefficient, square it, and add it to both sides. Doing this wraps that messy equation right back into a perfect square, revealing the hidden center and radius without crashing your brain.
Section 3. Lines, slopes, and intercepts. Connecting our points with straight lines requires us to understand the constant rate of change, also known as rise over run. Whether you're debugging a graph and can just eyeball the y-intercept, or you're only given 2 random points in the dark, these formulas let you instantly construct the exact line. Slope-intercept is perfect when you know where the line crosses the y-axis. Point-slope is your best friend when you just have the slope and a single random point. They look different, but algebraically, they execute the exact same logic.
Now, how do these lines interact? Parallel lines will literally never touch because their slopes, their steepness, are identical. Perpendicular lines, though, meet at a sharp 90-degree angle. Mathematically, we force that by making their slopes opposite reciprocals. If one line rises 3 and runs 4, the perpendicular line has to flip that fraction to 4 over 3 and flip the sign to negative. Section 4. What exactly is a function?
We are stepping up a level of abstraction here. We use equations all the time to draw shapes, but this brings up a fascinating question about what actually separates a basic relation from a true, formal mathematical function.
Think of a function like the biological mother rule. Just as every person has exactly one biological mother, a true mathematical function never assigns more than one output to a single input. Visually, this means it has to pass the vertical line test. If you drop a straight vertical line down your graph and it hits the curve in 2 different places, like it would on a circle, it throws an error. It's not a function.
For every function, we have to establish the constraints. The domain and range act as the shadow a graph casts on the x and y axes, showing every single valid input and output. When finding the domain algebraically, you're essentially writing error-handling code. You're keeping out values that break the rules of math. You can never allow an x value that divides by 0, and you can never allow an x value that puts a negative number inside an even square root.
Section 5, the function toolkit.
We need to stock our utility belt with the standard library of recognizable shapes. Recognizing these toolkit functions and their symmetries means you can instantly visualize the graph without tediously plotting a single point. See an absolute value sign? You instantly know it's a perfect V-shape with even symmetry across the y-axis. See a cubic function? You know it snakes upward with odd 180-degree rotational symmetry around the origin.
Memorizing these base shapes is crucial for fluency.
Finally, Section 6, Transforming Toolkit Functions.
Building on those base shapes, notice this brilliant, consistent pattern. Numerical changes sitting on the outside of the function alter the y-axis completely predictably. Adding moves it up, subtracting moves it down. But changes grouped inside the function, attached directly to the x, they alter the horizontal motion completely opposite to your intuition. Adding inside moves the graph to the left, not the right. It's a common trap, so watch out for it.
What's really cool here is how algebra proves our visual transformations are correct. Look at the square root function. If we put a 1/4 inside the function, our rule says it horizontally stretches the graph by the reciprocal, a factor of 4. But algebraically, the square root of 1/4 x is precisely equal to 1/2 times the square root of x on the outside. It flawlessly links a horizontal stretch directly to a vertical shrink.
We took raw mathematical coordinates and bent them into complex visual structures. You now have the fundamental logic to debug any geometric curve that comes your way. If you want to understand what the code says before it explodes, hit subscribe. Don't forget to like. This tells YouTube that technical content is still alive. Share this explainer with a beginner coder who needs help wrapping their head around this logic. And you, what did the code say in your project today?